In this section, I want to start talking about complex numbers, but we can't really get to complex numbers until we talk about imaginary numbers. And imaginary numbers are all based on a number called I, where I stands for imaginary. And there are exactly two important rules that you need to know about I. First of all, I, by definition, is equal to the square root of -1. Now, when we talk about real numbers and all values in the real number system, negative square roots, or I should say, the square roots of negative numbers, are not defined. But in the imaginary number system, they are. And that's why we can say that the imaginary number is equal to the square root of this negative number. We also say that when we square both sides of this, we get I squared is equal to -1. So we know these two values, we define them this way, and they can help us with lots of different things. But a really simple example from algebra is just the example of taking the square root of a negative number, where maybe, for instance, you're factoring a polynomial, you get down to the roots of that polynomial, and you end up with something like this. Maybe x is equal to positive or negative square root of, let's say, -25. So sometimes we'd end up with something like that. And if you got to that point, you're just stuck. You can't go any further. There's nothing you can do with this in real numbers only. But if you use imaginary numbers, you can simplify this further. What we can say instead of just square root of -25 is that -25 is the same thing as -1 multiplied by 25, right? We know that that's true. -1 times 25 is equal to -25, so we can rewrite it that way. And then by the rules for square roots, when we have the product of two values underneath one root, we can separate them into their own roots. So this is the same thing as the square root of -1 multiplied by the square root of +25. We know that the square root of +25 is 5, so we can get plus or minus 5 times the square root of -1. But now we've just defined the square root of -1 as I. So we can actually simplify this as plus or minus 5i. So before, in real numbers, if we had gotten to square root of -25, we'd be stuck. But in imaginary numbers, we can simplify that all the way down to positive or negative 5i. Another thing we want to make sure that we understand about imaginary numbers is that as we raise them to a different power, so obviously up here we have I to the first power, this is I to the second power. As we continue on, I to the third, I to the fourth, I to the fifth, and we keep going, the values of I are going to repeat. So if we pull these two out here, we already know that I to the first is equal to the square root of -1, and we know that I squared is equal to -1. We can also say that I to the 0, since we know any non-zero value raised to the 0 power is equal to 1, we know that this is equal to +1 as well. And if we want to find I to the third power, imaginary numbers follow the same exponent rules as real numbers. So I cubed is the same as I to the first multiplied by I to the second. And we already have I to the first and I to the second. So we have square root of -1 multiplied by -1, which is going to be equal to negative square root of -1. Or, since we know the square root of -1 is equal to I, we can call this -I. Now, if we continue on and we say I to the fourth, we know that's equal to I squared times I squared, and that's -1 times -1, or +1. If we look at I to the fifth, we know that that's I squared times I cubed, or -1 times a -I, which we know is a +1i, or just +I. If we say I to the sixth, we know that's I to the 4 times I squared, or +1 times -1, which is a -1. And if we say I to the seventh, we know I to the seventh is I to the 4th times I cubed, or 1 times a -I, which is a -I. What we're seeing here now is a repeating pattern. Here we have 1, and then I, and then -1, and then -I. Here we have 1, I, -1, and -I. And if we continue on, we'll get the same thing. So I to the 8th will be 1, I to the 9th will be I to the 10th will be -1, and I to the 11th will be -I. What this pattern allows you to do is simplify even large powers of I. So for instance, if we want to simplify, let's say, I to the 97, remember that every I to the 4th is equal to 1. So whenever we have a power like this, we want to just divide it by 4. What we realize is that 97 isn't divisible by 4, but 96 is. So if we rewrite this as I to the 96th times I to the 1st, and then I to the 96th is the same as I to the 4th raised to the 24th power, because 4 times 24 is 96, and then we have I here. I to the 4th we know is 1, so we get 1 to the 24th times I, and 1 raised to any power is still just 1, so we get 1 times I, or just I. So whenever you have I to a large power like this, you want to pull out from the exponent the largest possible multiple of 4. In this case with 97, it was 96, but if 96 wasn't divisible by 4, we would check 95 and then 94 and then 93 until we found a multiple of 4. Then we pull that out and we rewrite it as I to the 4th raised to whatever we have to multiply by 4 to get that exponent. And that way we can reduce that to 1 to whatever power, which is always just going to be 1. And so all you're going to have left then is just this value here, which in this case was I. Now when it comes to complex numbers, we always want to define a complex number like this. We say z is equal to a plus bi. And this is actually the rectangular form of a complex number. Complex numbers actually mix real numbers together with imaginary numbers. And when we look at a complex number given in this standard rectangular form, A is what we call the real part. This is the real part. And B specifically, not BI, but B specifically, is what we call the imaginary part, because that's the part that's with the imaginary number I. Sometimes when we talk about the real part of Z, we call that the real part of Z, and we call the imaginary part the imaginary part of Z, like this. So if you have a complex number, like Z equals 7 minus 6I, then the real part of Z is positive 7, and the imaginary part, you always have to remember to take the sign, is negative 6. So the imaginary part of Z is negative 6. So with complex numbers, you're always going to have this real part and this imaginary part, but sometimes the real part will be 0 or the imaginary part will be 0. So for instance, if the real part is 0, we would write that like this, 0 plus, let's say, just bi. We'll keep that imaginary part generic. But of course, this is going to simplify to just bi, and so the real part will disappear. And when the real part goes away because it's 0 and you're left with just the imaginary part, this number z equals bi, where b is any non-zero number, that's called a pure imaginary number. So pure imaginary. But then when we have the opposite scenario where b is equal to 0, the imaginary part is 0, and we have this, z is equal to a plus 0I, of course that's going to simplify to just a, and a is a real number, so we just have z equals a, and then we just call this a real number. Now the important thing that we want to realize is that every real number, if you have z equals a, every real number can be written as a complex number, because we can write it as z equals a plus 0I, and now it's just a complex number with a 0-valued imaginary part. And every pure imaginary number can also be written as a complex number, because we can just write z equals 0 plus bi, and the real part is just 0. So every pure imaginary number and every real number is still a complex number, because they can both be written in this complex form. But in the particular case where the real part is 0, then we have a pure imaginary number. And in the particular case where the imaginary part is 0, then we have a real number. Just like with real numbers, we want to be able to do arithmetic with complex numbers, including addition, subtraction, multiplication, and division. So let's go ahead and start by talking about addition with complex numbers. So when you add two complex numbers together, let's say that we have 2 plus 3i, and we have negative 4 minus 6i. When we want to add those two together, we simply add their real parts together and their imaginary parts together. So the sum will be 2 plus a negative 4, which is the same as 2 minus 4. And then we add to that the sum of the imaginary parts. So 3i, and then plus a negative 6i is the same as minus 6i. So we're just adding the real parts and we're adding the imaginary parts. 2 minus 4 is a negative 2. 3i minus 6i is a negative 3i. So we get plus negative 3i or just minus 3i. So the sum of these two complex numbers is negative 2 minus 3i. Now subtraction of complex numbers is going to be the same thing. When we have two complex numbers and we want to find their difference, we just find the difference of the real parts and then separately the difference of the imaginary parts. So for instance, if we were going to subtract negative 4 minus 6i from 2 minus 3i, let's go ahead and write that out. We have 2 plus 3i minus negative 4 minus 6i. So we're finding the difference. We're subtracting the second one from the first. We just find the difference of the real numbers. So 2 minus a negative 4. And then we add to that the difference of the imaginary parts. So we say 3i minus a negative 6i. So minus negative 6i. 2 minus a negative 4 is 2 plus 4. And then 3i minus a negative 6i is 3i plus 6i. And we could really keep parentheses around these. 2 plus 4 is 6. And then 3i plus 6i is 9i. So the difference of these two, 2 plus 3i minus negative 4 minus 6i, is 6 plus 9i. Keep in mind also that we could have just distributed this negative sign. So we could have taken everything out of the parentheses and just said 2 plus 3i, and then minus a negative 4 is plus 4, minus a negative 6i is plus 6i, and then just grouped together like terms. So group together the real terms, 2 plus 4 is 6. Group together the imaginary terms, 3i plus 6i is 9i, and we find the difference that way as well. When we want to multiply, so let's say multiplication, we can multiply either real numbers, imaginary numbers, or some mixture of the two. So we know that if we have something like 4 times 5, two real numbers, that's 20. Well, if one of these is imaginary, like 5 is 5i instead, we still just multiply the coefficient on the I by the 4. 4 times 5 is 20, and we just get 20i. If we multiply two imaginary numbers together, so we say 4i times 5i, we still just multiply the 4 and the 5, and then we multiply the I times the I, and we get I squared. But we know from before that I squared is equal to negative 1. So this actually gets us 20 times negative 1, or negative 20. So we always want to look, whenever we end up with i's in our final answer, we want to look to see if we can simplify it at all. And in the case of I squared, that's always negative 1. So we can always change I squared to negative 1 and simplify this. So 4i times 5i, multiplying two imaginary numbers, results in the real number value, negative 20. So here we had two real numbers, one real number and one imaginary number, and two imaginary numbers, and we know how to multiply those. Sometimes also, though, we're going to have some kind of binomial multiplication, like for instance, we might have 4 plus 5i multiplied by 2 minus 3i. So we have binomial multiplication of complex numbers. We're multiplying the complex number 4 plus 5i by the complex number 2 minus 3i. So how do we do that? Well, we're going to do it the same way as if we had real number binomials. We're going to use FOIL, first, outer, inner, last, to multiply these out. So we just need to multiply the first values together, 4 times 2. So we'll get 4 times 2. Then the outer values, 4 and negative 3i. So, and we're always adding in between, 4 times negative 3i. then the inner values 5i and 2, so plus 5i times 2, and then the last values, 5i and negative 3i, so 5i and negative 3i. And then we just simplify everything out. 4 times 2 is 8. 4 times a negative 3i, we saw up here when we multiply, is a negative 12i. 5i times 2 is 10i. And 5i times negative 3i is a minus 15i squared. So we'll get 8. We have these like terms here of negative 12i and positive 10i. So we have addition here of imaginary numbers. Negative 12 plus 10 is a negative 2, so those sum to a negative 2i. And then we know here that with negative 15i squared is equal to negative 1. Negative 15 times a negative 1 is a positive 15, so we get plus 15. 8 plus 15 is 23, so we get 23 minus 2i, and we end up with the complex number 23 minus 2i, which is the product of 4 plus 5i and 2 minus 3i. Now for division with complex numbers, we'll need a little bit more room. If we start with a complex number like 2 plus 3i, and we want to divide that by a real number, let's say we divide it by 4, this is going to be like any fraction division problem that we're used to. We just split up the fraction because we have 2 terms in the numerator. Divided by 1 denominator, we can split these up. So this is the same as saying 2 over 4 plus 3i over 4. And 2 over 4 we can reduce to 1/2. So we end up with 1/2 plus, we can leave it as 3i over 4, or we can just say 3/4 I, so that we can easily identify 1/2 as the real part and 3/4 is the imaginary part. So that's what happens when we divide a complex number by a real number. It's going to be similar if we divide a complex number by an imaginary number. Let's say we divide by the imaginary number 4i. Well, same thing, we can split up the fractions. So we get 2 over 4i plus 3i over 4i. In this case, for the second fraction, we'll get I to cancel from the numerator and denominator, leaving us with just 3/4. For the first fraction, we'll bring this I to the numerator because this I is I to the first power. If we bring it to the numerator, we just have to change the sign on the exponent. So instead of I to the first in the denominator, we'll get I to the negative 1 in the numerator. So we can rewrite this as 2 over 4 I to the negative 1 plus 3/4. Then I to the negative 1, if we follow our pattern, remember before we talked about the pattern of these I values, we said that I to the first power was the square root of negative 1. We said that I to the second power was negative 1. We said that I to the third power was negative I. And we said that I to the fourth power was positive 1, and that kept repeating. So I to the fifth would then be square root of negative 1 again. I to the sixth would be negative 1, and we could keep going in this direction. We also knew that I to the 0 was going to be 1, and so you see the pattern repeating in this direction as well. Well, the same goes for negative exponents. Here we have I to the exponent of negative 1. If we take our exponents this way, the next value in the pattern should be negative I. I to the negative 2 would be negative 1. I to the negative 3 would be square root of negative I, and the pattern can continue on this way for negative exponents. So I to the negative 1 is going to be a negative I. So this will be, let's reduce our fraction 2 over 4 to 1/2. So 1/2 times a negative I plus 3 over 4. And then if we rewrite this in rectangular form for a complex number, 3/4 is the real part, so we'll move that out to the front. We'll move the negative sign out and get a minus 1/2 times I. So 3/4 is the real part, negative 1/2 is the imaginary part. That's what happens when we divide by this imaginary number. But what happens when we divide by a complex number? So let's say we have 2 plus 3i, and we want to divide that by 1 minus 6i. Now at first, the way that we're going to handle this is going to seem a little bit like a trick, but you'll see why it works in just a second. So what we want to do to divide this complex number by the 1 in the denominator is actually multiply this fraction by what we call the complex conjugate of the denominator. In this case, that's 1 plus 6i, and so we want to multiply both the numerator and the denominator by 1 plus 6i. So how did we get 1 plus 6i? Well, all we do to find the complex conjugate of a complex number is we keep the two terms the same. So here we have 1 and 6i. Just ignore the sign in the middle completely and look at 1 and 6i. Here we have subtraction, so we just want to change that to addition. In other words, you leave the two terms the same and you just change the sign in the middle. So the complex conjugate of 1 minus 6i is 1 plus 6i. The complex conjugate of 2 plus 3i would be 2 minus 3i, because we'd keep the 2 and keep the 3i, and we just change the sign in the middle. In this case, we have addition, so we would change it to subtraction, and the complex conjugate would be 2 minus 3i. So that's how you find a complex conjugate, and when we multiply both the numerator and denominator by the complex conjugate of the denominator, let's see what we get. Here in the numerator, we end up with 2 plus 3i times 1 plus 6i, and then in the denominator, we'll end up with 1 minus 6i times 1 plus 6i. Let's work on the denominator down here. If we FOIL this out, we take 1 times 1 and we get 1. 1 plus 6i is plus 6i. Negative 6i times 1 is negative 6i. And negative 6i times a positive 6i is minus 36i squared. And here's what the trick is of the complex conjugate. Whenever you multiply by the complex conjugate, you're always going to end up with these two terms here in the denominator, a positive version of the term and a negative version of the term that will cancel with each other. So these are going to change depending on the problem, but these two middle terms in the denominator will always cancel. Furthermore, when you have this 36i squared here, remember that I squared is the same thing as negative 1, so we can rewrite this as negative 1. We get negative 36 times negative 1 is a positive 36, so we end up with 1 plus 36, or 37. And so what happens every time when you have this kind of fraction here and you multiply by that complex conjugate, it's going to change the denominator from a complex number that includes an imaginary number into a real number. So we're changing from an imaginary value to a real value, and that is the benefit of multiplying by this complex conjugate. So this will be our denominator, but let's go ahead and look at the numerator. So when we FOIL out the numerator, we're going to get 2 times 1 is 2. 2 times 6i is 12i. 3i times 1 is 3i, and 3i times 6i is an 18i squared, and we know already from working on the denominator that we're going to end up with a positive 37 in the denominator. And then we can simplify further here and say 12i plus 3i is 15i, so 2 plus 15i. We know that I squared is negative 1. Negative 1 times 18 is a negative 18, so minus 18 all over 37. And then 2 minus 18 is a negative 16, so negative 16 plus 15i all over 37. And then we can go ahead and split up the fraction. So the final answer is negative 16 over 37 for the real part, plus 15 over 37 multiplied by I for the imaginary part. And this is the result of this complex number division, 2 plus 3i divided by 1 minus 6i. You might not think so at first, but we can actually graph complex numbers in a really straightforward way, similar to the way that we graph rectangular coordinate points. So we just graph them in what we call the complex plane rather than the Cartesian plane or in the XY plane. So we call this here the complex plane. And the complex plane has a horizontal axis that represents the real numbers and a vertical axis that represents the imaginary numbers. In the same way that in rectangular coordinate space, the horizontal axis is represented by x, the vertical axis is represented by y. So if we want to graph a complex number, let's say for instance we want to graph 5 plus 2i, the real part is a positive 5. So we head out toward the positive direction of the real axis, which is the right-hand side. So just like the xy plane, the positive half of the real axis is over here on the right, the negative half is on the left. The positive part of the imaginary axis is the top, the negative part is the bottom. So positive 5 on the real axis is 1, 2, 3, 4, 5 right here. And then positive 2 on the imaginary axis, we just head up 1, 2 in the positive direction of the imaginary axis, and that point is right there. Now what if we wanted to graph, let's say, negative 3 minus 3i? Well, the real part is negative 3, so we'd head out toward the negative direction, 1, 2, 3, negative 3 right here. And then the imaginary part is also negative 3. So we head down toward the negative half of the imaginary axis, and we go down 1, 2, 3 to negative 3, and that point is right there. You'll also run into situations where the real part or the imaginary part is 0. So let's say we want to graph 4i. Well, in that case, the real part is 0. So we stay right here at the origin for the real part, and then we just go up 4 units in the positive direction of the imaginary axis, 1, 2, 3, 4, and that point is going to be right here. So if it's a pure imaginary number, the number will be on the imaginary axis somewhere. And then similarly, if we have a real number, let's say we want to graph negative 2, then we go out toward the negative direction of the real axis to negative 2, and then because the imaginary part is 0i, we don't go in the positive direction, we don't go in the negative direction, we just stay right here, and that point we graph right there. And so if it's a real number, it'll be on the real axis. Keep in mind too that when you're graphing complex numbers, you'll also be asked to do lots of problems where you graph, for instance, the sum of two complex numbers. So let's say we want to graph the sum of these first two complex numbers here. The first thing we want to do is take the sum. We want to say 5 plus 2i plus negative 3 minus 3i and add those complex numbers together. So if we simplify, we get 5 plus 2i minus 3 minus 3i, just taking those parentheses away. 5 minus 3 is 2. 2i minus 3i is minus I. So we get the number 2 minus I. And if we graph that, the real part is positive 2, so we head out positive 2, and the imaginary part is minus 1. So we get minus 1, and that is this point right here. So this point is the sum of this white point here and this blue point here. And you could also graph the difference of two complex numbers. In that case, we would get 5 plus 2i minus negative 3 minus 3i. If we distribute the negative sign, we get 5 plus 2i minus a negative 3 is plus 3, minus a negative 3i is plus 3i. 5 plus 3 is 8. 2i plus 3i is 5i. So we have the point 8 plus 5i. So if we go out to there, 1, 2, 3, 4, 5, 6, 7, 8 will be right about here. And then plus 5 will be 1, 2, 3, 4, 5, maybe right about here. So the difference of those 2 points, this point here, the white point, minus the blue point, gets us up to here, which is the difference. So we'll call this the difference, and we'll call this the sum of those 2 points. So just be aware that you can find the sum or the difference of complex numbers and then graph those in the same complex plane. So in previous math classes, you probably learned how to find the distance between 2 points using the distance formula. But even if you haven't, it's really simple and we'll review it here, so it's okay if this is the first time you're seeing it. Let's say that we have 2 points in coordinate space, and instead of using the real and imaginary axes, let's just pretend that this is the xy plane instead. So if we have a point here, maybe, this would be the point 2, 1. So we'll say this is 2, 1. And then let's say we maybe have a point 1, 2, 3, 4, 5, maybe at 5, 3. How about that? So this will be 5, 3 right here, 5, 3. And we can use the distance formula to find the distance between 2 points. But before we find that distance, we want to recognize why this formula is working. It's based on the Pythagorean theorem. So this is the distance that we're looking for here. But what we want to realize is that this distance here is related to the horizontal and vertical distances between these 2 points. So we could say that the horizontal distance between these points is something that looks like this, and the vertical distance is something that looks like this. And what we see is that we have a right triangle. And so if we have a right triangle, we can say that we have here side lengths of A, B, and C. And then we know by the Pythagorean theorem that a squared plus b squared is equal to c squared, that's always true for a right triangle. Since this point here is at x equals 2 and this point here is at x equals 5, the horizontal distance, or a, between these 2 points is 5 minus 2. And so we could say that this is 5 minus 2 squared. And the vertical distance, since this point is at y equals 1 and this point is at y equals 3, the vertical distance is 3 minus 1, so 3 minus 1 squared. And then that's going to be equal to c squared. And so, of course, we could calculate that as 5 minus 2 is 3, 3 squared is 9, 3 minus 1 is 2, 2 squared is 4, so plus 4 equals c squared, or 13 equals c squared, or if we take the square root of both sides, we get c is equal to the square root of 13. And so we know then that the distance between these two is the square root of 13. But really, we could generalize this formula. So if we look at this formula right here, what we realize is that we're really subtracting the two x values from one another. So we could say instead that this is, let's say, x sub 2 minus x sub 1 squared. We're finding the difference between the y values, so we could call that y sub 2 minus y sub 1 squared. And let's say instead of c, we want to call the distance between the 2 points d, then we could call this d squared. And then if we simply take the square root of both sides, we get d is equal to the square root of this entire left-hand side, x sub 2 minus x sub 1 quantity squared, plus y sub 2 minus y sub 1 quantity squared. And the result there is the distance formula. So this is the distance formula that we use to calculate the distance between any 2 points. The cool thing is that this distance formula also works for complex numbers. So let's say this time that we have the complex numbers, maybe 1, 2, 3, 4, and 1, 2. So we'll call this complex point here, and now we're in the complex plane where we have the real axis and the imaginary axis. We'll call this negative 4 plus 2i. And then maybe we have the complex number 3 minus 3i. So maybe right here, and we'll say this is 3 minus 3i. So the distance between those two is this distance right here. But remember, we could break this up into a vertical distance that comes down here to maybe negative 3 like that, and then a horizontal distance that comes from negative 4 over to 3 parallel to the real axis. Now we can use the distance formula, or we can just recognize here that the distance between negative 4 and positive 3 along the real axis, if we have a distance of 4 right here and a distance of 3 right here, then the full distance of the two together is 7. And here along the imaginary axis, if we have a distance here of 3, because we had this negative 3i, so from the real axis down to this point is a distance of 3 units. And then up here to plus 2i, this is a distance of 2 units. Then those two distances together are 5 units. And so still in that case, looking at this right triangle, we have the 2 legs, and we can plug these into the Pythagorean theorem and say 5 squared plus 7 squared is equal to the length of the hypotenuse, or the distance between the points, we'll say d squared. So 25 plus 49 is d squared. 74 is d squared, or the distance between the points is square root 74. And we found the distance between the complex points, noticing that it's still a real number, just like when we found the distance between the 2 points in the xy plane. Here in the complex plane, when we're dealing with complex numbers, we still have a real value for the distance. And that's because we're still just talking about a distance in space, and so we can express that as a real number. We don't need an imaginary number in order to express the distance between those. If instead we had wanted to plug those complex numbers into the distance formula, we could have done so. The x values are the real values, and the y values are the imaginary values. So for x sub 2 minus x sub 1, we could say 3 minus a negative 4, so 3 minus a negative 4. And then for the y values, we'd use the imaginary parts. And so for the imaginary parts, we could say negative 3, we don't need the I, just negative 3 minus this positive 2. So minus 2 squared, and that would be equal to 3 minus a negative 4 is 3 plus 4, which is 7. 7 squared is 49. And then negative 3 minus 2 is a negative 5. Negative 5 squared is a positive 25, so plus 25. And then we would get from that the square root of 74, and that would be the value for the distance between the points. So if you want to just use the distance formula, instead of drawing this triangle, even though they're really doing the same thing, just take the real parts and the imaginary parts, plug those real parts in for x and the imaginary parts in for y, and use that formula to calculate the distance. Now that we know how to find the distance between 2 points, finding the midpoint of that distance is going to be just as simple. So if we want to find the midpoint between 2 complex numbers, we're simply looking for the middle of this distance here. So we have this point in the complex plane. We're looking for the point that is midway or exactly halfway between those 2 points. To find it, all we have to do is look at the horizontal and vertical distances separately. So we know that the horizontal distance between the points is 7. We got that right here. So if we want to find the horizontal midpoint, if you will, we just take that and divide it by 2. So 7 divided by 2 is 7 halves, or 3.5. Then we just count over 3.5 units either from this point or from this point horizontally. So if we started with negative 4 over here, we could count over 3.5 units, 1, 2, 3.5, and we'd wind up about here. Or we could start at this point 3 and count over 3.5 units, and we'd end up at 1, 2, 3.5, the same spot. So 3.5 units from the horizontal distance or along the real axis is going to be right about here. And we know that that's at negative 1/2. So the real part of the midpoint is going to be negative 1/2. Then if we look at the imaginary parts, we know the vertical distance between these 2 complex numbers is this value here, 5. We already found that. So again, we divide that by 2, and we say 5 divided by 2 is equal to 2.5. So again, we can start from here and count down vertically 2.5, or start from here and count up vertically 2.5. So here, if we start at 2 and we go down 2.5, 1, 2.5 gets us to this negative half value right here. If we start at negative 3, the imaginary part down here, and we count up 2.5, we get 1, 2.5, the same spot, up to negative 1/2. That means the imaginary part is going to be negative 1/2, so we get minus 1/2 I. So the midpoint between negative 4 plus 2i and 3 minus 3i is the complex number negative 1/2 minus 1/2 I. And if we graph that, the point that we find is this point right here. We didn't do a perfect job graphing it, but this point right here, which is on this hypotenuse or on this length here between the two complex numbers, and it's exactly in the middle of this distance that we found earlier. When we talk about expressing a complex number in polar form, what we mean by polar form is in the polar coordinate system. So, as you know, we're used to working with rectangular coordinates. Normally we have a coordinate system like this one, and we call this the x-axis, we call this the y-axis. And the way that we locate points in rectangular coordinate space is by looking at the horizontal distance from the origin and the vertical distance from the origin. So for instance, if we have a point here at 1, 2, 3, 4, 1, 2, 3, so maybe that point is right here, we say that that is 4 horizontal units from the origin and 3 vertical units from the origin, so it's at the rectangular coordinate point 4, 3. And that's certainly one way to locate points in coordinate space. But in polar form, we locate points in coordinate space in a different way. We, first of all, consider the distance from the origin directly. So instead of going horizontally and then vertically, or vertically and then horizontally, we start at the origin and we go directly to the point. So we go out to the point here, and that direct distance straight from the origin, we call that distance r, and that is just the distance from the origin, which we also call the magnitude or the modulus of this point. And then we can also consider the angle between this point here and the positive direction of the x-axis. So if we look at this angle here, and we call that the angle theta, now we can put together any values of theta and r, and if we just have theta and r, we're able to locate any point in coordinate space in the same way that we can locate any coordinate point in rectangular space using rectangular coordinates x and y. We can do the same thing if we just have r and theta. The first thing we want to be able to do now that we know about polar form is to convert from rectangular form to polar form. So if we are given a point in rectangular coordinate space like 4, 3, how do we convert it to a point in terms of r and theta? The reason that we want to do that, remember, is because if we actually call this the complex plane, and we say that this is the real axis, and this is the imaginary axis, then this point here, 4, 3, is actually the complex number z equals 4 plus 3i. So being able to convert from 4, 3, or 4 plus 3i, to polar coordinates is going to allow us to convert this complex number, 4 plus 3i, into something in terms of r and theta. So the way that we're going to find r is using the Pythagorean theorem. What we want to recognize is that we have a right triangle. So if we just connect this point down to the horizontal axis, we have essentially here the horizontal distance a and the vertical distance b. And then because this is a right triangle, I know from the Pythagorean theorem that a squared plus b squared is equal to c squared. And if I solve for c, which is the length of the hypotenuse, I do that by taking the square root of both sides, and I get c is equal to the square root of a squared plus b squared. But I know because I want to express this in polar coordinates, and the length of this hypotenuse here I've called r as the distance from the origin, I can instead write this as r equals the square root of a squared plus b squared. Sometimes we'll write r as the magnitude or the modulus of the complex number z, which we write like this. It looks like the absolute value of the complex number z. And this just means distance from the origin of the complex number z. And that's, of course, the same thing, the square root of a squared plus b squared, like this. So if we want to find the magnitude of the complex number 4 plus 3i, we know that this horizontal distance is 4. We know that the vertical distance is 3. So we can plug those into our formula and get the square root of 4 squared plus 3 squared, or the square root of 16 plus 9, which is the square root of 25, and we know the square root of 25 is 5. So we can say that the distance from the origin is 5. The length of this hypotenuse here is 5. Now that we have a value for r, all we need is the angle theta. And the angle theta is going to come from what we know about trigonometry. If we remember the rule SOHCAHTOA, which tells us that sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent, we can find a value for theta. If this is the angle theta here, we already know the length of the opposite side, that's b, and we already know the length of the adjacent side, that's a. So since we have opposite and adjacent coming directly from the complex number 4 plus 3i, we have opposite and adjacent, we want to go ahead and use tangent. So we can say that tangent of theta is equal to opposite over adjacent, or if we take the arctangent of both sides, we'll get arctangent of tangent of theta is equal to arctan of opposite over adjacent, and then we're able to get arctangent to cancel with tangent, leaving us with just theta on this side. So we get theta is equal to arctan of opposite over adjacent. And that's how we come up with a formula for theta. So we really have these two formulas that we want to remember. We have this formula to find r, and we have this formula to find theta. In this case, the length of our opposite side is 3, the length of our adjacent side is 4, so we're going to get theta is equal to arctan of 3 over 4. If we want, we can get a decimal approximation for this, and we can say theta is approximately, if we round to the nearest degree, 37 degrees. Now that we have a value for theta and a value for r, we can put this into polar form. Now, how do we come up with the polar form for a complex number? Well, we can derive the formula if we want to. We start with the complex number z equals a plus bi. And if we go back here to our SOHCAHTOA rule from trigonometry, we can build out the pieces that we need for a and b. So for instance, if we say sine is equal to opposite over hypotenuse, which it always is, so sine of theta is equal to opposite over hypotenuse. But we know that the opposite side from theta is b, and we know that the hypotenuse is r. We call the hypotenuse r. So we have sine of theta equals b over r. If we multiply both sides by r, we get b equals r sine theta. We can do the same thing for cosine. We know that cosine is equal to adjacent over hypotenuse. So if we say cosine of theta is adjacent over hypotenuse, well, the adjacent side to theta is a, and the hypotenuse is r, so we get a over r. And again, if we multiply both sides by r, we get a is equal to r cosine theta. Now we can plug these values for a and b into our complex number equation z equals a plus bi. So we get z is equal to r cosine theta, coming from the value for a, plus r sine theta, coming from the value for b, multiplied by I. If we factor out an r to simplify this and move the I in front of the sine theta, we get r multiplied by cosine theta plus I sine theta. And this expression here is what we recognize as the polar form of a complex number. So this is the formula that we're going to use. You don't have to derive it every time from these values of a and b. We're just going to go ahead and plug directly into this formula. So given this, now we have values for theta and for r, we can say that the polar form of z equals 4 plus 3i is z equals r, which we found was 5, so 5 times cosine of theta, which we know is about 37 degrees, so 37 degrees, plus I sine of 37 degrees, and this is the polar form of z equals 4 plus 3i. So both of these values are the same. It's just two different ways of expressing exactly the same point. Keep in mind here that when we found arctan of 3/4, we didn't get a clean value in radians, so we converted to degrees. But sometimes you'll get a clean value in radians, and if you do, you can go ahead and leave this value in terms of radians instead of converting the angle to degrees. But either way, whether these angles here are in degrees or radians, this is the polar form of this same complex number we were given. Now that we know how to express a complex number in polar form, we need to talk about how to multiply and divide complex numbers when they're given to us in polar form. So for instance, if we're given two complex numbers, we'll call them z sub 1 and z sub 2. They'll of course look like this if they're in polar form. You'll recognize this. We have the distance from the origin r, and then we have the angle theta between the positive direction of the x-axis, or the real axis, and the point in the complex plane. So this is the polar form of a complex number, and we have two of them, and we've just given these values as r sub 1 and r sub 2, and theta sub 1 and theta sub 2 so that we can keep track of them. And we want to show what it looks like to multiply or divide two of these values. So let's look first at multiplying these 2 points together and what happens, because we can actually come up with a formula that is going to give us the product of two complex numbers every time. So if we want to multiply these, of course the product of z sub 1 and z sub 2 we can express as z sub 1 times z sub 2. And then we're basically multiplying these right-hand sides. So if I take this right-hand side and I multiply it by this right-hand side, I can pull r sub 1 and r sub 2 out in front because those are going to get multiplied together. And these two binomial terms are going to get multiplied together as well. So I can have cosine theta 1 plus I sine theta 1 multiplied by cosine theta 2 plus I sine theta 2. And now I have two binomial terms, so I can actually just FOIL those out. I multiply the first terms together, cosine theta 1 times cosine theta 2. So I get cosine theta 1, cosine theta 2. And then I take the outer terms, cosine theta 1 and I sine theta 2. So I'll say plus I cosine theta 1 and sine theta 2. Then I take my inner terms, I sine theta 1 and cosine theta 2, and multiply those together. So I sine theta 1, cosine theta 2, and then the last terms, I sine theta 1 and I sine theta 2. When I multiply the i's together, I'm going to get I squared, and then I'll have sine of theta 1 and sine of theta 2. And this is the product of these two complex numbers. The first thing I want to do here is recognize that this I squared term is equal to negative 1. We know I squared is equal to negative 1. So we can get rid of that there and just write this as minus 1, or minus sine theta 1 sine theta 2. Then we want to group together the imaginary and real parts. So I still have r1, r2. And then my real parts will be this first term, cosine theta 1, cosine theta 2, and then my last term here, minus sine theta 1, sine theta 2, and then my imaginary parts will be these two middle terms here. Now if I factor out the I, I'm simply left with cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2, and I have my I here on the outside. Now this part comes directly from trig identities, and it's the part that helps us simplify this expression the most. When you have this value here, cosine times cosine of two different angles, minus sine times sine of the same two angles, so basically cosine A, cosine B, minus sine A, sine B, that's the form that we have here, that's always equal to cosine of A plus B, or in this case, theta sub 1 plus theta sub 2. This is a trigonometric identity that tells us that these expressions are equal to one another. And the same thing goes here when you have cosine times sine plus cosine times sine, and it's the same two angles, just reversed. You have cosine of theta 1 and then cosine theta 2 over here, and sine theta 2 and sine theta 1. That's always equal to sine of theta 1 plus theta 2. So we can say plus we'll pull the I out in front and say I sine of theta sub 1 plus theta sub 2. Now here's what we want to notice about this formula we just found. If we go ahead and move this up here, and then we take our formula that we just found here, and we move that up here, what we see is that this formula for the product of two complex numbers actually has the same form as a single complex number in polar form. We have this value out in front, just like here we have r sub 1 out in front. We have cosine of something plus I sine of something, just like we have cosine of something plus I sine of something. So what we want to realize is that when we take the product of two complex numbers, the r value, the value we're going to get out in front, is simply equal to the product of these two r values here. And then the angle theta is always just going to be theta sub 1 plus theta sub 2 coming directly from these two angles here, theta sub 1 and theta sub 2. So instead of going through this whole process, we can just delete everything that we did. The formula that we're always going to use for multiplying two complex numbers is just here. And we take r sub 1 times r sub 2, and then we follow the same pattern, cosine of theta sub 1 plus theta sub 2, which we get from these angles, plus I sine of the same angle. Now when it comes to dividing two complex numbers, the formula we can find in a similar way. So what we would do is to get the quotient of z sub 1 and z sub 2, we would say z sub 1 divided by z sub 2 will be equal to, and then you just divide the right-hand sides by each other. So we say r sub 1 times cosine of theta sub 1 plus I sine of theta sub 1. And then we divide that by the right side of z sub 2. So r sub 2 cosine of theta sub 2 plus I sine of theta sub 2. And then to solve this in the same way that we found the formula for the product of complex numbers, we would actually multiply this fraction on the right by the complex conjugate of the denominator. So we would multiply by both the numerator and denominator cosine theta sub 2 minus I sine of theta sub 2. So we're taking the denominator, cosine theta sub 2 plus I sine theta sub 2, and the complex conjugate of that is the same two terms, but with a different sign in the middle. So instead of addition here, we have subtraction. And we multiply both the numerator and the denominator by that same value, like this. And I won't go through all the math, but what happens when you do that is that you'll be able to get terms to cancel in the denominator. Eventually, you'll be able to simplify, and you'll be able to use trigonometric identities to simplify to a formula like this one. And so what we're going to get then for the formula for division of complex numbers is r sub 1 divided by r sub 2, and then that's all multiplied by cosine of theta sub 1 minus theta sub 2 plus I sine of theta sub 1 minus theta sub 2. And so in a similar way here, we have, just like the product, we end up with the quotient of the two r values out in front, and we end up with the difference of the two angles, theta sub 1 minus theta sub 2, for both cosine and sine. So instead of having to go through this whole process and find the formula, we can just go ahead and use this formula straight away if we're given two complex numbers. So for instance, to do an example, let's say we have z sub 1 equals 10 times cosine pi over 2 plus I sine pi over 2. And then for z sub 2, we have 5 times cosine of 3 pi over 2 plus I sine of 3 pi over 2. And we want to find the product and the quotient of the two complex numbers. Well, the product, let's go ahead and say the product will be equal to, we'll take the product of z sub 1 and z sub 2, and we'll say z sub 1 times z sub 2 is equal to, And following our formula, we take the two r values and multiply them together. 10 times 5 gives us 50. And then here we have cosine of theta sub 1 plus theta sub 2. Well, in our case, that's pi over 2 plus 3 pi over 2. That gives us 4 pi over 2 when we add them together, which is the same as 2 pi. So we get cosine of 2 pi plus, following our formula here, I sine of the same angle, so sine of 2 pi. So we can leave the product in this form, which is in polar form, or you could evaluate cosine and sine at the angle 2 pi and simplify this back into rectangular form if you chose to. Here's what that would look like. We would say 50 multiplied by cosine of 2 pi is 1, sine of 2 pi is 0, so 1 plus 0i. That's going to be equal to 0i is 0, 1 plus 0 is 1. That's equal to 50. So in rectangular form, we could write that as 50 plus 0i. And so we know that this is a real number that's going to sit on the positive half of the real axis. So 50, or just 50 plus 0i, both of those are equivalent to 50 times cosine 2 pi plus I sine 2 pi, which is the product of these two complex numbers. And then if we want to find the quotient, we'll again follow our formula for the quotient of two complex numbers, and we'll say z sub 1 divided by z sub 2 is equal to, we'll take r sub 1 divided by r sub 2, or 10 divided by 5. Well, 10 divided by 5 is 2, so we get 2 out in front, and then we'll say cosine of theta 1 minus theta 2. Well, that's pi over 2 minus 3 pi over 2. So 1 pi over 2 minus 3 pi over 2 is a negative 2 pi over 2, or just a negative pi. So we're going to get negative pi plus, if we're following our quotient formula here, I sine of the same angle, so negative pi. This is the quotient of the complex numbers in polar form, and again, we could leave it this way, or we could put it back into rectangular form by evaluating cosine and sine at these angles. So we could say cosine of negative pi is a negative 1, so we'll get negative 1 here. Sine of a negative pi is 0, so plus 0i, and that's just going to leave us with a negative 2, which we know is going to be on the negative side of the real axis. So this is a real number sitting on the negative side of the real axis, or we could write that as negative 2 plus 0i. Either way, that's how you use the formulas for the product and quotient of two complex numbers to find in polar form this product z sub 1, z sub 2, and the quotient z sub 1 over z sub 2 when you're given two complex numbers. We learned in the last lesson how to find the product of two complex numbers. So given two complex numbers z sub 1 and z sub 2, we said that the product of those two complex numbers was given by this expression here on the right-hand side. And what we learned was that when we took the modulus or magnitude of each of those complex numbers, r, in each of those equations, that we would multiply those together out in front here, and that we would simply add the angles from the complex number to get the new angles. What we want to talk about here is finding the power of a complex number. For instance, if we have a complex number and we want to square it or raise it to the third power, fourth power, fifth power, how we go about doing that. And the reason that we're talking about that now is because, of course, if we were to find something like z to the fifth, that's just the same as multiplying z by itself 5 times. So we multiply z by itself 5 times, and we already know, we just learned, how to multiply two complex numbers together. So what we're really saying is, what happens to this formula when we keep multiplying the same complex number by itself over and over and over again? Well, the cool thing is we can just adapt the product formula. So let's start with this formula and instead pretend that we're multiplying z sub 1 by z sub 1. Well, in that case, on the left-hand side here, instead of z1, z2, we'll get z1, z1 is equal to, and then instead of r sub 1, r sub 2, we'll get r sub 1 times r sub 1. And then instead of theta sub 1 and theta sub 2, we'll have theta sub 1 for both. So we'll get theta sub 1 plus theta sub 1 plus I sine of theta sub 1 plus theta sub 1. And the result there is r sub 1 squared times cosine of theta sub 1 plus theta sub 1 is 2 theta sub 1 plus I sine of 2 theta sub 1. And that's, of course, equal to z sub 1 squared. Now, if we want to find z sub 1 cubed, we multiply z sub 1 by itself again. We're simply going to be multiplying this value again by r sub 1 here in the front. So we'll end up with r sub 1 cubed. And here we'll have 2 theta sub 1 plus another theta sub 1, again coming from the extra z sub 1 value. So we'll end up with cosine of 3 theta sub 1 plus I sine of 3 theta sub 1. And if we were to keep going and we find z sub 1 to the fourth, we want to find the fourth power, we'll get r sub 1 to the fourth cosine of 4 theta sub 1 plus I sine of 4 theta sub 1. And so hopefully what you're starting to see is that if we raise this complex number to the power of 2, we're going to be raising r to the power of 2, and we're going to get a coefficient here on the angle of 2. If I want to raise z to the power of 3, I'm going to get an exponent of 3 here on the r, and I'm going to get coefficients of 3 on the angle. And if I want to raise this to the fourth power, I'm going to end up with r to the fourth, and I'm going to end up with a coefficient of 4. And we could keep doing this and we'd follow the same pattern. And so what we can extrapolate from this is that if I want to raise a complex number to the n power, regardless here of the value of n, the result will be r to the n multiplied by cosine of n theta plus I sine of n theta, like this. And this right here, this formula right here, is what we call De Moivre's theorem. And I'm going to say that wrong because it's French, but we'll go with De Moivre's theorem. So this is the theorem that De Moivre came up with, and it basically gives us a formula to find any power of a complex number. So for instance, let's take an example. Let's say we have the complex number z is equal to, we'll say, 2 times cosine of maybe 5 pi over 4 plus I sine of 5 pi over 4. So we've been given a complex number in polar form, and now we're asked, let's say, find z to the sixth power. Well, instead of using this product formula and multiplying this out 6 times, we can go straight to De Moivre's theorem and say that z to the sixth must be equal to, we take the modulus of 2 and we raise that to the sixth power, so that must be 2 to the sixth, times cosine of, the n value here is 6, so we get 6 times 5 pi over 4. So this will be 6 times 5 pi over 4 plus I sine of 6 times 5 pi over 4. And then we can simplify. 2 to the sixth is 64. Here for the angle, 6 times 5 pi is 30 pi. 30 pi over 4 we can reduce to 15 pi over 2. So we'll say cosine of 15 pi over 2 plus I sine of 15 pi over 2. Now we could leave the answer in this form, but it's nice to give an angle that's in the interval 0 to 2 pi, the principal angle. 15 pi over 2 is 7.5 pi, that's outside of 2 pi. So if we find the coterminal angle with 15 pi over 2 that's in that interval, it's going to be 3 pi over 2. And so we could write this as 64 times cosine of 3 pi over 2 plus I sine of 3 pi over 2. And this then, by De Moivre's theorem, is z to the sixth power when z, the complex number, was this value here. Now, as always, we can leave the answer in polar form. We can say z to the sixth is equal to this number in polar form, or we could evaluate cosine and sine at 3 pi over 2 and put this in rectangular form. So we could say z to the 6th is equal to cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. So we get minus 1i, or just minus I, and that's equal to 64 times -i, or just -64i. That tells us that z to the 6th power is a complex number, or a pure imaginary number, and because we have this negative I value, it's going to be on the negative half of the imaginary axis in the complex plane. So we could plot z to the 6th power there as -64i. So whether you leave the number in polar form or you convert it to rectangular form, either way is fine. But that's how you use De Moivre's theorem to find a power of a complex number. In this video, we want to talk about how to solve complex number equations, and we're going to need to be able to do this because it's going to lead into the next lesson about finding the roots of a complex number. So the easiest way to understand this is to simply walk through an example. Let's say, for instance, that we're given an equation like this. Let's say z cubed is equal to 64. This is a complex equation because first, it's an equation, and second, it involves the complex number z. When we say that we want to solve this complex equation, we want to solve it for all of the different complex numbers z that make this equation true. Those complex numbers can sometimes be pure imaginary numbers or sometimes real numbers, but either way, we want to find all of the complex values z that will make z cubed equals 64 a true equation. So the way that we're going to do it is by looking kind of at the left-hand side in isolation and the right-hand side in isolation. If we start with the left-hand side, z cubed takes us straight back to De Moivre's theorem. This is De Moivre's theorem here, and we know that when we have the complex number raised to a power, that it expands out this way. So z cubed is the same thing as if we plug n equals 3 into the right-hand side of this equation. That's the same thing as r cubed times cosine of 3 theta plus I sine of 3 theta. So in z cubed equals 64, we've just replaced the left-hand side, z cubed, with this value, which comes straight from De Moivre's theorem. Now, if we look at the right-hand side, 64, we know that we can rewrite 64 as 64 plus 0i. That's the rectangular form of the complex number 64. From this, we know that a is 64 and that b is 0. And so if we want to then put this in polar form, we really put z cubed in polar form. Now we're trying to put 64 in polar form. If we put 64 into polar form, we have to first find r. So r we know is going to be equal to the square root of a squared plus b squared. So we'll get 64 squared plus 0 squared. And 0 squared obviously is going to be 0, so we'll end up with the square root of 64 squared. Well, the square root and the exponent of squared, or 2, those two things are going to cancel. So the square root of 64 squared is just 64. So that's the value of r, but then we need to find the value for theta. So theta, as we know, is arctan of b over a. Well, in this case, b over a is 0 over 64, and 0 over 64 is just 0, so we get arctan of 0. Well, arctangent of 0 is 0, so our value of theta will be 0. Therefore, if we want to write 64, the complex number 64, in polar form, we can write it this way. We can say z is equal to the value of r, 64, times cosine of theta, which is 0, plus I sine theta, or I sine 0. Now, this is a little tricky here, but we know that the angle 0, we came up with theta equals 0, theta is an angle, so we have the angle 0. 0 is also coterminal with the angles 2 pi, 4 pi, 6 pi, 8 pi. If we keep adding 2 pi, we get the same angle, theta. All those angles are coterminal. So instead of just writing cosine of 0 and sine of 0, we could really say that this is going to be the same complex number if we have cosine of 0 or 2 pi or 4 pi, etc., if we keep going, plus I sine of the same thing, 0 or 2 pi, or 4 pi, or 6 pi, 8 pi, etc. Now, if we factor out a 2 pi from each of these, so let's look at this one here, 0, 2 pi, 4 pi, 6 pi, etc. If we take out a 2 pi here, 2 pi times 0 gives us 0, 2 pi times 1 gives us 2 pi, 2 pi times 2 gives us 4 pi. So if we pull out that 2 pi, we're going to get 0, 1, 2, 3, 4, etc. So then if we just call k any non-negative integer, then we can really replace this whole string 0, 1, 2, 3, 4 with a value of k, as long as we say that k is a non-negative integer. So we can really express this as z is equal to 64 times cosine of 2 pi k plus I sine of 2 pi k. This equation is obviously given in radians, but we could also express this in degrees. We could say 64 times cosine of 2 pi is the same as 360 degrees. So 360 degrees times k plus I sine of 360 degrees times k. This value here that we found is the same as the complex number 64, or 64 plus 0i. We just rewrote it in polar form and gave a general expression that includes all these coterminal angles. So really, since this value is equal to 64, we could replace the right-hand side of this equation, 64, with this value that we just found. So if we do that, we said that this value was z cubed, and so we already replaced the left-hand side of this equation, and so if we replace the right-hand side, we say that this whole thing here is equal to 64 times cosine of 360 degrees times k plus I sine of 360 degrees times k. And now, replacing both the left and right-hand sides of z cubed equals 64 is really helpful, because what we see is that we have the same format on the left-hand side as we do on the right-hand side. We have this value out in front here on both sides, and on both sides we have cosine of the angle plus I sine of the angle. And so we can say that the angle and the angle here. And what we can conclude from that is that in order for these two sides to be equal, these values in blue have to be equal and these values in red have to be equal. Otherwise, since they're in exactly the same format, otherwise the equation would not be true, which means we're able to pull from this a system of equations. And this process we're following is the same process you can follow every time to solve a complex number equation like this one. So what we get next, our next step, is to get this system of equations, r cubed equals 64, and 3 theta is equal to 360 degrees times k. Now r cubed equals 64, we can solve. We get r is equal to 4, because 4 cubed is 64. And to get theta, we just divide both sides by 3, and we get theta equals 120 degrees k. Now remember we said that k was a non-negative integer, so 0, 1, 2, 3, 4, etc. So if we start plugging in values for k, at k equals 0, we're going to get theta equals 0 times 120 degrees, or 0 degrees. If we get k equals 1, we'll say 1 times 120 degrees, or 120 degrees. At k equals 2, we'll get theta equals 240 degrees. And at k equals 3, we'll get theta equals 360 degrees. However, 360 degrees and 0 degrees are coterminal with each other, so we've already gotten back to the same value we found for k equals 0. And if we continued on, we would get 480 degrees, which is coterminal with 120. And then we would get 600 degrees, which is coterminal with 240. And we would keep circling back around and around and around, getting coterminal angles with 0, 120, and 240, which is totally not necessary. All we need are these first 3, because everything after that is just an angle that's coterminal with one of these first three. So we're going to pay attention only to these first three. And what we want to do then is take these values for theta and this value that we found for r, and we want to plug them into the polar form of a complex number. So the first value we get is z equals, we take the value of r, 4 times, and this is just the standard form for a complex number, 4 times cosine of theta, or cosine of 0 degrees, plus I sine of 0 degrees. And if we simplify that, cosine of 0 is 1, so we get 4 times 1. Sine of 0 is 0, so plus 0i. And the result there is just 4. We'll call that z sub 1. For z sub 2, we tried 0 degrees, now we have to do 120 degrees. We'll get 4 times cosine of 120 degrees plus I sine of 120 degrees. And then we get 4 times cosine of 120 is negative 1/2, and sine of 120 is root 3 over 2, so root 3 over 2. So if we factor out a 2, we'll get 4/2 times negative 1 plus root 3 times I. 4 over 2 is 2, so we get 2 times a negative 1, negative 2 plus 2 root 3 times I. And that's the value associated with 120 degrees. And then we just need theta equals 240 degrees. So we'll call this z sub 3. And we'll get 4 times cosine of 240 degrees plus I sine of 240 degrees, which is equal to 4 cosine of 240 is negative 1/2. And sine of 240 is negative root 3 over 2, so negative root 3 over 2. And then if we factor out the 2 in the denominator, or in fact we'll take out the negative and then 2 in the denominator, we'll get negative 4 over 2 times 1 plus root 3 times I. Negative 4 over 2 is negative 2, and when we distribute that across, we'll get negative 2 minus 2 root 3 times I. What this tells us then is that there are 3 complex numbers, z sub 1, z sub 2, and z sub 3, that will make this equation true. In other words, these 3 values here, 4, negative 2 plus 2 root 3i, and negative 2 minus 2 root 3i, all 3 of those complex numbers are solutions to the equation z cubed equals 64. The 4 should make intuitive sense because we know that 4 cubed is equal to 64. If we plug in 4 for z, we get 4 cubed, and that's equal to 64, and we know that. But these 2 values here are complex numbers that, when plugged in for z, will give you a result of 64. And if you want to, go ahead and try these 2 values, plug them for z. You'll have to cube them, which you can do using De Moivre's theorem or the formula for the product of complex numbers. And you'll see that when you actually multiply those out, you get a value of 64. And so that's how you find the solutions to a complex number equation. In the last video, we talked about how to solve complex number equations. And we started with the complex equation z cubed equals 64. And we transformed both sides of the equation to put them into polar form. Here what I've done is shown the same equation, just with the right-hand side changed into polar form. So this 64 times the quantity cosine 360 degrees k plus I sine of 360 degrees k, this whole expression on the right-hand side is the same thing, it has the exact same value as 64. It's just written in polar form. So these 2 equations are actually equivalent. When we solved for the values of z that make this equation true, these were the values that we found, and we left these complex numbers in polar form. But the reason that I'm bringing all of these equations from the previous video into this video is because we want to see that there's a pattern to finding the values that make the equation true. And when we have a complex equation like this, where we have z to the 3rd power equals 64, when we say that we're finding the values of z that make this equation true, what we're really doing is taking the 3rd root of each side, because if we wanted to solve this for z, we could simply take the third root of both sides. So we could say the third root of the left-hand side, z cubed, is equal to the third root of the right-hand side, and then the third root of z cubed is simply z, so we get z is equal to the third root of 64. Now we can look at this and probably see that the third root of 64 is equal to 4, because we know that 4 times 4 times 4, or 4 cubed, is 64. So we know that one value that makes the equation true is z equals 4. But there are also complex numbers that are not just real numbers, but include an imaginary component that are going to make this equation true. And the three values that make this equation true are these values that we found down here below. This first one, z sub 1, this turned out to be the real number 4, the one that we see here. And then these two values, z sub 2 and z sub 3, gave us the two complex numbers that make this equation true, that satisfy this equation for z. The way that we rewrote this equation, z cubed equals 64, in this way here with the right-hand side transformed, that it almost looks like there's a pattern when we find the solutions of z. For instance, here I always have 4 in front, and 4 is always the third root of 64. I have z cubed. I'm looking for the third root of z cubed. I have the third root of 64. And I can see that I have 360 degrees times k here. Well, 360, if I divide that by 3, again, this seeming magic number 3, I get 120 degrees, which is the difference between all of these angles here. 0 plus 120 is 120, plus 120 is 240. 240 plus 120 gets me back to 360. So there's clearly something going on here. And if we extrapolate this formula to find the roots for z, what we say is that when I want the nth roots of z, so for instance, if I want the third roots of this equation, I say the nth roots of z is equal to the nth root of r, and then I multiply that by cosine of theta plus 360 degrees times k divided by n plus I sine of the same angle, theta plus 360k divided by n. And this is the formula that will always give us the nth roots of a complex number z. So let's say, for the sake of an example, that I want to find, let's say, the third roots. So we're going to find the third roots of this complex number. Z equals 125 times cosine of 90 degrees plus I sine of 90 degrees. So I have a complex number in polar form. I want to find the third roots of this. Well, if I'm finding third roots, that means that n equals 3. You're always going to have the same number of roots as what you're asked for here. So if I'm looking for third roots, there's going to be 3. If I'm looking for fifth roots, there's going to be 5. If I'm looking for 10th roots, there's going to be 10 of them. So n equals 3, and if I plug into my formula, I'm going to say that the third roots of z, which is what I want, is going to be equal to the third roots of r. In our case, r is 125, then multiplied by cosine. Here's where I plug in my angle theta. So in this case, theta is 90 degrees. So I want to say 90 degrees plus 360 degrees times k, all divided by n equals 3. And then the same thing plus I sine of 90 degrees plus 360 degrees times k divided by 3. And now I have my equation set up to find the third roots of z. So the third root of 125 is 5. And then before we start actually finding roots, I can still simplify what's inside here a little bit. So because 90 and 360 are both divisible by 3, I can divide 3 evenly into those and say cosine of 30 degrees plus 120 degrees times k plus I sine of the same thing. So 30 degrees plus 120 degrees k. And now I have my expression simplified. All we need to know now to find the roots are the values of k. And keep in mind that k always starts at 0. So because I'm looking for n equals 3, and k starts at 0, I'm going to say k equals 0, k equals 1, and k equals 2. Now I have 1, 2, 3 roots, so I stop. And the pattern there is because k always starts at 0, your last k value is always going to be 1 less than the value of n. See that 2 here is 1 less than 3? That's always going to be the case because you have the same number of roots and because k always starts at 0. So these are the 3 values for k that we need to plug into this expression for the third roots of z. So the first third root of z, we could say the third root of z, and we'll say that this is associated with k equals 0. That's going to be given by whatever we get when we plug 0 into this expression here. So I'm going to get 5 multiplied by, here 120 times 0 is 0, 0 plus 30 is 30, so I'm going to get cosine of 30 degrees, and then the same thing here, plus I sine of 30 degrees. Now I could leave the root in this form, or I could simplify it by evaluating cosine and sine at 30 degrees. Cosine of 30 degrees is root 3 over 2, and sine of 30 degrees is 1/2. So basically this is going to be equal to 5 root 3 over 2 plus 5 times 1/2, or 5/2 I. I can find the third root associated with k equals 1, so the third root of z associated with k equals 1 is going to be equal to, again plugging into this expression here, 5 times cosine, here I plug in k equals 1, 1 times 120 is 120, plus 30 is 150, so cosine of 150 degrees plus I sine of 150 degrees, and that's going to be equal to, cosine of 150 is negative root 3 over 2, so I'm going to end up with negative 5 root 3 over 2, and sine of 150 is positive 1/2 again, so I'm going to end up with 5 times 1/2, or 5/2 I. And then the last root, third root of z associated with k equals 2, which is our last k value here, that's going to be 5 times, when I plug in k equals 2, 2 times 120 is 240, 240 plus 30 is 270, so cosine of 270 degrees plus I sine of 270 degrees. Cosine of 270 is 0, so that term will drop away. Sine of 270 is negative 1, so I'll get negative 5i, negative 5i. What we found then through this process, using this formula for the roots of a complex number, is the 3 third roots of this complex number given here, z equals 125 cosine of 90 plus I sine of 90. The interesting thing is that these 3 roots are actually going to divide the circle with radius 5 because r equals 5 right here. They're going to divide the circle with radius 5 into 3 equal pieces. So imagine cutting a pie that has radius 5 into 3 equal pieces. That's where you're going to find these roots. In other words, if I draw a super basic circle, something that looks like this, so we have graph here, and then we'll put a circle on this, something like that. We'll say that this circle has radius 5, so this right here, in other words, would be the point 5, 0, and this point here would be 0, 5. These 3 third roots here, if we graph them, they'll be about here, and I'm just doing this roughly, about here, and about here, because these 3, and this one is obvious down here, this negative 5i. Negative 5i is, of course, going to be on the negative half of the imaginary axis, which is down here. So if I divide this circle by like connecting these points like this and like this, these are roughly 3 equal sections, section 1, section 2, section 3, and it's 3 equal sections because we have third roots. So this would be the point here, 5 root 3 over 2 plus 5/2 I. This would be negative 5 root 3 over 2 plus 5/2 I. And this would be the point down here, negative 5i. So that's what it means to find the nth roots of a complex number. Given the complex number in polar form, you can find the nth roots for any positive integer value of n using this formula here for the roots of a complex number, and those nth roots will divide the circle with radius r into n equally sized pieces.